Okay, so what we saw so far is that you can actually use the catalog of the responses and calculate the. So let's see if we can actually do this. And in the process of doing this, we will see that we are missing one thing still. And we'll develop that, and then we'll be all ready to go. So let's try to do an example that I've drawn here. So it's h of t. Let's say the system impulse response looks like that, and you're trying to determine its output to this one. We know how to do this with convolution, doing convolution in time domain. But let's see if we can convert these to the equivalent operator domain and see if we can use the operator domain. So first of all, we have to write this in terms of elementary functions because we want to express it in terms of those. So how do we write this in terms of elementary functions? Well, you have a step here first. So you can write it as u of t, and then you have to have a negative ramp minus t u of t or r of t. And that would keep going all the way down. So you have to stop it at 1. So then you have to have a plus t minus 1 u of t minus 1, which is r of t minus 1. This is r of t minus 1. Right? Agreed? That I can write that in those terms. The other thing that I have here, so this is, and this one is pretty simple. This is just u of t. So the question is that what are the associated operators for this? So if I were to write h of p and x of p to multiply them to get the y of p, what are they? So x of p is pretty straightforward. What is x of p? What is the operator that generates u of t off of an impulse? 1 over p, right? So that's easy. What is h of p? So the first term is 1 over p, right? What is the second term? Minus 1 over p squared, right? What is the third one? What do you do with that? It's a delay, right? It's not happening at time t. It's happening at time t minus 1, or at t equals 1 as opposed to t. So what is that? What's the operator associated with that? Or in general, what is the operator associated with the delay? So up until now, we don't know how to deal with this, right? I mean, what do we do with this? Because we can't really write it as another 1 over p, because then basically it cannot be 1 over p squared, right? Because if it were that, it would just cancel each other and you would get just neither one. So what is it? What is that delay in the operator? So let's leave this here for a second. We'll come back to it. So I use this to motivate this discussion of delay, because this is the last piece of the puzzle, really. If you know how to deal with delays and time shifts, essentially, then you can do anything with them. So the last piece of the puzzle is this. So let's say your h of t, the impulse response, of course, of the system, is the system operator operating on the delta, by definition. Right? So now the question is, what is the impulse response of h of t minus tau in terms of that? So what is that? Well, you can write the Taylor series expansion, or Maclaurin expansion more accurately, of this. This is a function, right? H of t. Tau is some constant. Tau is the delay, right? 3, 5, 7, some number. And t is the variable. So I can write it, express this as h of t, right? Plus, rather minus, because of this thing, minus tau, h prime of t, right? It's a Taylor series expansion, if you will. Plus tau squared over 2 factorial h double prime of t minus tau cubed over 3 factorial h triple prime, and so on and so forth, right? So you agree that this series expansion is associated with that. So now let's see if we can do one-to-one transfer from this to the operator domain. So we want to see what these correspond to. So what I would do, so what is the associated operator with this? It's just h of p, right? Agreed? What is the operator associated with this? So this is tau. This is a derivative of h, right? Wouldn't this be tau p h of p? Because capital H of p produces that h of t off of an impulse, and then you put an p up front, you take in the derivative. Right? Agreed? And the next term is tau squared 2 factorial. This is a 2. Very ugly looking 2. Okay. 2 factorial p squared h of p. Would be minus tau cubed 3 factorial p cubed h of p, and so on and so forth. So what you see here is that actually you can write this whole thing as h of p, or rather 1 minus tau p plus tau p squared over 2 factorial minus tau p cubed over 3 factorial plus blah, 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 times h of p, right? So what is this? Does anyone recognize this as something that has a more compact form? Go ahead, yeah?
Oh, I just know it's I think it's the
e to the negative tau p, tau, right? But because think about it, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial all the way up. So e to the negative p or tau p is going to be 1 minus tau p plus tau p squared over 2 factorial minus tau p cubed over 3 factorial all the way up, right? So this is nothing but e to the negative tau p h of p. So in other words, h of t minus tau is going to be this operating on the delta of t. So a time shift, a delay in time, corresponds to an exponential e to the negative tau p. Now, this exponential, right, this is an exponential because this is basically just writing it as a sum of polynomials. It also has the properties of exponential. You can explicitly, for example, show that e to the tau 1p, e to the tau 2p equals e to the tau 1 plus tau 2p, which makes sense if this were a delay, right? It's a think about this as a cascade of two systems, one with delay tau 1 and one with delay tau 2. If the first system delays your input by tau 1 and the second one delays it by tau 2, the aggregate system should delay it by tau 1 plus tau 2, right? Which is, if it were an exponential, would do it. And you can actually explicitly prove this. And the proof of this is basically writing these as the series, right? You can say this is tau 1p plus, this is actually negative, but I'll drop the minus signs for a second. So there's a negative delay. This is an advancement in time. Tau 1 p1 squared over 2 factorial, blah, 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 and then multiply by tau 2p plus tau 2p squared over 2 factorial, etc., etc., etc. And if you multiply it out, you will see that it will become 1 plus tau 1 tau 2p plus tau 1 squared plus 2 factorial tau 1 tau 2 plus tau 2 squared over 2 factorial p squared, which basically gives you tau 1 plus tau 2 squared over factorial. So you can see that this becomes essentially e to the tau 1 plus tau 2 p. So it has the property that it needs to have. So when in this operator domain you multiply, if you have two cascaded systems with delays, right? What is the impulse response of a system with a delay, by the way? What is the impulse system response if this is a delay system, delay of tau 1? If an impulse comes at, what's its impulse response like? It's an impulse at tau 1, right? It delays the impulse by tau 1. So now if you have two of them in cascade, you will have another one that would be shifted by tau 2, and then the overall response would be shifted by tau 1 plus tau 2, right? So the same thing is true in the operator domain. If one had a delay of, really, if you want it to be a delay, this has to be negatives. Of e to the negative tau 1p, e to the negative tau 2t, then you get an aggregate delay. Okay? So this is useful and important. So now let's bring it back to come back to our example. So now what do? Now we know how to deal with this, right? So what is the next term? it's this guy with the delay, which is multiplied by e to the negative, well, the delay is 1 in this case, so it would be e to the negative p, right? 1 over p squared. So that's that last term. So how do I calculate the output? That's the objective, right? So we did develop that. So if I wanted to find the output for this, it's going to be obviously the product. We argued that it's the product. That was the one with 2 boxes, I guess. Which is what? What's the product of these two? 1 over p squared minus 1 over p cubed plus e to the negative p 1 over p cubed. And then I have to convert that back to a y of t, right? Again, I use the catalog. What is the catalog entry for this one? P squared? R of t, or t u of t. What is the catalog entry for this one? What is it? T squared over 2. Exactly. And what is the catalog entry for this? Now with the delay, with our knowledge of the delay, how it's treated. So this is a delay. This will delay it, right? Whatever this is multiplied by its delay. So what was this to begin with? It's this guy, right? So you just get that delayed by t. So you replace the t with t minus 1. So it would be the same thing, except for the fact that you replace the t with t minus 1. So that's your response. That's the convolution of those two things. And if you actually do the convolution, you will see. If you do the convolution the old-fashioned way, you will see. Actually, I believe you've done this example before. Right? So that's what we've been building up to, the ability to do these kind of things. And it's very important, again, because it allows you to do this calculation in a certain way. And more importantly than just doing the calculations, it gives you additional insight when it comes to design about how to choose these later on. For example, if you want a system that does a certain kind of, changes the input in a certain way, you have another way to think about it. If you want to make a low-pass filter, if you want to make an equalizer, if you want to make something that changes the property of a system, if you want something that takes out a certain property of it and presents it to you in a certain way, you can do all of that with something like this. All right. Any questions? All right. Well, I guess I'll see you next time.